So the best linear unbiased estimator really is a good way to go. That's why it's called best. Actually, it's called best because it minimizes the error given some statistical description of the error, of the observation error. So what if we have some measurements that are more reliable than others? In general, that's one of the things we can use blue for. But another way of solving this is to let r equal y minus ax. We're going to call this the residual, and we want to minimize WR squared, which is just equal to WY minus WAX squared, where W is some weighting matrix. And it's usually diagonal. In other words, if there are measurements that you want to give more weight to, you use this weighting matrix. The solution, the weighted least squares solution, is just equal to WA pseudo inverse times WY, which is could also be expressed as XWLS is equal to A transpose W transpose WA, when WA is full rank, times A transpose W transpose W times Y. So weighted least squares works if for some reason some measurements are more important than others, or perhaps measurements are measuring different quantities that have different units. You want to normalize the response. Weighted least squares is a good basic solution. Before we go too much further, what happens, so this is no longer just weighted least squares, back to blue. What if the expected value of E transpose equal to R is diagonal? Where R is equal to maybe nu squared times I. We know that our blue solution is equal to A transpose R inverse A inverse A transpose R inverse Y. So in this case, we get A transpose let's say 1 over nu squared here. A transpose A inverse times A transpose 1 over nu squared times y. These two values cancel, and that just gives us A transpose A inverse A transpose y when A is full rank. This is our basically standard least squares solution. So just one other example. Okay, we're next going to talk about ways to efficiently compute our least square solutions. So see you at next lecture.